You're watching Electrical Engineering Lectures channel. For more videos, please do like, subscribe, and hit the bell icon for the latest notifications.
Assalamu alaikum everyone. In today's lecture of digital communication, we will be discussing the concept of bandpass modulation, and specifically we will be talking about coherent detection of phase shift keying. In the previous lecture, we have already discussed in detail the concept of coherent detection along with the coherent detection of amplitude shift keying. So what is coherent detection? Just as review, I am telling you again that the coherent detection is the process in which the receiver uses the information of carrier phase to perform the demodulation on the received signals. So the other counterpart of this coherent detection is non-coherent demodulation, which does not require or which does not uses the knowledge of carrier phase to perform demodulation or detection. And we also discussed in the previous lecture the categorization of bandpass modulation schemes into three types: one-dimensional, two-dimensional, and multi-dimensional. In today's lecture, we will be talking about two-dimensional waveforms. Specifically, in that case, we will discuss M-ary phase shift keying. So what is the general model of phase shift keying? Before going into the mathematics, let us discuss the main concept behind phase shift keying. As amplitude shift keying is the analogous or counterpart of amplitude modulation, similarly phase shift keying is the sister modulation scheme in digital communication as compared to the phase modulation used in analog communication. So the main concept is to change the phase of the carrier in accordance with the amplitude of the message signals. Since we are in digital domain, so the message symbols are here digital and they are only finite in numbers. So the carrier will experience a phase change in accordance with each of the transmitted symbols. Amplitude and frequency will not change. So therefore, if you see that the ith transmitted symbol will be equal to 2es over t square root, here you can see there is no indication of I in the amplitude. It means that the amplitude of this carrier will be fixed and it will not be changed with respect to the amplitude of the message signal. And similarly, inside the argument of cause, frequency will not change and there is only the index I appearing in place of the phase, which is 2 pi I over m. So for simplicity, we can say it as phi I. So it is the phase of the ith symbol, which is equal to 2 pi I over m. And since it belongs to the category of two-dimensional modulation, the reason behind is that it requires at most two basis functions to represent each of the transmitted pulse. And those two basis functions are psi 1 of t, which is 2 over t square root cos omega ct, and the second one is psi 2 of t, which is minus 2 over t square root sine omega c t. So these are two completely orthogonal basis functions, and each of the transmitted waveforms from I is equal to 1 to capital M, they can be represented by the linear combination of these two basis functions by using this particular equation, where AI1 and AI2 are correspondingly the weights, and those weights are specified by this thing, AI1 and AI2. So by combining these weights and these two basis functions, you can come up with ith transmitted waveform corresponding to the M-ary phase shift keying. Now, one important point that need to be kept in mind is that the energy of each symbol in case of M-ary PSK will be the same because the amplitude is not changing. That is why the symbol energy will be equal to the ith symbol energy, and that will be obtained through the square of the norm of ith symbol vector. So that is the difference between PSK and ASK. In ASK, we have seen that the amplitude and the symbol energy of each of the constellation point was different from all the others. But in case of PSK, the amplitude and the energy of the constellation points of each of the PSK symbols will always be the same. They will not depend on the value of I. Now, as an example, first of all, we talk about Bpsk, which is binary phase shift keying. So, binary phase shift keying, which is Bpsk, for which m is equal to 2. Now, the equation was Si of t is equal to AI1 psi 1 of t plus AI2 psi2 of t for I is equal to 1 to capital M, where psi1 of t was 2 over t square root cos omega ct. Psi2 of t, which is orthogonal to psi1, it was minus 2 over t sine omega c t. And the values of ai1 was es square root cos phi I, and ai2 was es square root sine phi I, where phi I is equal to 2 pi I over capital M. So in case of binary phase shift keying, what are the values of phi I? So we can only have I is equal to 1, for which phi 1 comes out to be 2 pi into 1 divided by 2. So that will be cancelled out and we will have phi is equal to pi. And the second one is I is equal to 2, which means phi 2 will be equal to 2 pi into 2 divided by 2. So that will be cancelled out and we will have 2 pi, which is equivalent to 0. So we will have these two phases. Either we will have a phase of pi or we will have a phase of 0. So if we put these phases in the transmit pulse Si of t, that comes out to be 2Es over capital T cos omega ct plus 0, corresponding to I is equal to 2, and Si of t, or we can say it S2 of t, and S1 of t will be equal to 2Es over capital T into cos omega ct plus pi, and that is basically minus 2Es over capital T into cos omega c t. So you see, there is only the difference of plus and minus. If you compare these two, there is only a difference of plus and minus in case of binary phase shift keying. Due to this reason, you can always say that instead of using two basis functions for binary phase shift keying or Bpsk, you only require a single basis function, which is psi1 of t. So both of these can be represented by using only one basis function, which is psi1 of t. Due to this reason, this binary phase shift keying is very much similar to the case of one-dimensional schemes, because it is only using one basis function. But the point to be considered is that for higher order modulations, for m greater than 2, we will be requiring two basis functions which need to be orthogonal, right? So now what about the constellation diagram? If you see the constellation diagram, the values of ai1, because these are the amplitudes of the constellation points. So ai1 comes out to be es cos phi I. So for I is equal to 1, we will have a11 as es into cos of 0 or cos of pi. You can say any one as pi and the other one as 0. So it will be minus es square root. And for I is equal to 2, you will have a12, and that will be equal to es square root cos of 0, which comes out to be es square root. So you see, the magnitude of both these points will be the same. So the constellation diagram comes out to be this one. It will be only along the x-axis. You will have 2 points. The amplitude of one point is es square root, and the second one is minus es square root. So these are the two constellation points with the amplitudes of es square root and minus es square root. So you see, the magnitude of these 2 points are the same. The only difference is the angle. And you see the beauty of this mathematical model, that it has automatically placed these 2 points maximum far apart from each other. Because from the complete angle of 360 degree or 2 pi, maximum distance that these 2 points can attain from each other is 180 degree. So it is very much clear here that both these points are pi radians apart from each other. This is due to the fact that we want to have such modulation scheme in case of phase shift keying that we can have maximum we can have these 2 points which are maximum apart from each other, so that the performance improves in case of the presence of noise, right? So if any symbol now occurs in this complete plane, if any symbol occurs in these 2 quadrants, it will be detected as the first symbol, and if it is located in the other 2 quadrants, it will be detected as the other symbol. So the complete decision region consists of 2 quadrants, the first quadrant and fourth quadrant. This is first decision region, and the second quadrant and third quadrant, they constitute the second decision region, right? So similarly, if you extend this concept for higher order modulations for m is equal to 4 and m is equal to 8. So let me just tell you about m is equal to 4. For m is equal to 4, if you find out the angles, angle was phi I is equal to 2 pi I over capital M. You see, for m is equal to 4, they will also be placed maximum far apart from each other, because if you divide 360 degree into 4 parts, it will be having 90 degree. So each decision region will be containing 90 degree of the entire plane. So for I is equal to 1, we will have phi 1 equals 2 pi divided by 4 as pi by 2. Similarly, for I is equal to 2, we will have phi 2 is equal to 2 pi into 2 divided by 4. It will have pi. For I is equal to 3, we will have phi 3 equals 3 pi by 2. And for I is equal to 4, we will have phi 4 equals 2 pi, which is again 0. So now the constellation diagram will have 4 points, and you need to have 2 basis function in this particular case. This basis function is phi 1 of t, and this basis function is for phi 2 of t, and the constellation points will be like this: the first point, the second point, third point, and the fourth point, right? So this point is corresponding to 0 0, it is 0 1, it is 1 1, and it is 1 0. But the main point is that the energy or the amplitude of each of these points is the same, which is Es square root. So magnitude will also be the same. So they will be in the form of a circle like this, circle having radius of Es square root, Es magnitude square root. So that is the formation of the constellation diagram. Similarly, you can extend for m is equal to 8, and for m is equal to 8, you can see this particular constellation, and at this time it is again in the form of a circle of radius Es magnitude, Es square root, and we will have 8 constellation points, and each constellation point is pi by 4 radians apart from the other constellation point, to make the decision regions maximum apart as possible. So before considering the general architecture of M-array phase shift keying receiver, we talk about the case for binary phase shift keying, because in binary phase shift keying it is very much similar to the case of one-dimensional case. So therefore it can be simply understood with the help of matched filter receiver. And if you remember, the matched filter concept was that on the receiver side, in each of the branch we perform the filtering with a filter which is matched to the transmitted pulse, matched to each transmitted pulse. So for S1 of t, we will have a matched filter on the receiver side. For S2 of t, we will have the second matched filter, and so on up to m matched filters. Or in case of basis functions, we will have n matched filters, because we are talking about binary phase shift keying, and we consider the match filtering in case of 2 branches, right? So the analog version of the match filter is this one, which simply says that the impulse response of the match filter is flipped and shifted version of the transmitted pulse. So it will be S of capital T minus T, where capital T is the symbol period. If you discretize this particular system, the complete, because in implementation you do not use analog descriptions. In implementation you always use digital versions of all the filters, right, for the implementation of digital transmitter and digital receiver. So the model will look like this. R of k will be equal to Si of k plus N of k, where N of k is the noise, AWGN. And we are talking about binary, so I is equal to 1 to k, and this the small k are the time indices. So if you look at the receiver model, the received signal is first passed through Nyquist filter. So this particular filter is called Nyquist filter having bandwidth of W equal to 1 over 2 TS, where TS is sampling time, and then the received data is sampled at a rate T is equal to K TS, means integral multiples of the sampling period, and once each sample comes, it is basically R of K, and it is being stored over here in this register. Now these are the coefficients of the match filter, and through the theory of the match filter we have to decide what are the coefficients of the match filter, because the continuous domain version was S of capital T minus T, and in each capital T now you have got total n samples, capital N samples, capital N samples. So the discrete time version of match filter will look like this: S of n minus 1 minus n, because the whole duration 0 to capital T is being converted from 0 to n minus 1, right? So in place of T you will have n minus 1, and therefore the discrete time version will be like this. Again, flipping will be there, shifting will be there, but now for n is equal to 4, let's say we select n is equal to 4. So for n is equal to 4, the equation comes out to be this. So for each value of n, you will substitute the coefficients by using this particular equation, right? So from C0 to Cn minus 1, we will have total n coefficients, and the purpose of match filter will be to perform convolution between the received data and these coefficients. And basically, what is convolution? Convolution means flipping. So we have all these coefficients already in the flipped format, right? Now we take an example. For example, if we have two waveforms, because we are considering binary case, S1 of t, which is cos omega naught t, and S2 of t, we have just seen that there is a difference of only a negative sign. So if one is cos omega naught t, the other one will be minus cos omega naught t. If the first waveform look like this, so that is first sample is here, second is here, third is here, and fourth is here. Similarly, for this particular thing, the first one is here, second is here, third is here, and fourth is here. So the match filter structure will have two branches. In the first branch, and let's suppose that the received pulse at this particular symbol period is S1. So the same received data will be convolved with the match filter coefficients in both the branches, and the branch which will give the maximum answer, that corresponding symbol will be detected as the received symbol, right? So you see, in both the branches, in the first branch and in the second branch, we have filled both the branches with S1. So you see, the first one is 1, 0, minus 1, 0. These are corresponding to these values: 1, 0, minus 1, and 0. These are the four samples. The same four samples are filled over here: 1, 0, minus 1, and 0. What about the coefficients? In each branch, the coefficients will be matched to one of the waveforms. So in the first branch, the coefficients are matched with S1. So they are S1 of 3 minus n. And here they are matched with S2. So S2 of 3 minus n, right? So you see, now you can just check and put the values, because the equation was C of n equal to S of 3 minus n. Let's say we are talking about S1. So for n is equal to 0, C1 of 0 will be equal to S1 of 3. So here you see, C1 of 0 will be equal to S1 of 3. S1 of 3 was 0, so this 0 is here. Similarly, you can compute all the values by putting the values of n, and you fill out all these coefficients by using S1 over here and by using S2 over here. And then you simply perform multiplication and addition by using the equation of convolution here, and you add them together. So you see, 1 into 1, 1. This is 0, this is again 1, this is 0. So overall the sum is 2, and that is the answer. So Z1 at k is equal to 3 is equal to 2. And similarly, in the second branch, you perform the same multiplication and addition, and at this time, this 1 into minus 1, it is minus 1. It is, the second one is 0, then minus 1, then 0. So overall the answer is 2. Overall the sum is minus 2. So now you see, you have got two answers to be fed into the detection stage. The first answer is 2 and the second answer is minus 2. So because it is binary case, thresholding will only contain a one threshold, and that threshold is 0, or simply find the maximum of these two, and since the maximum is this one, so due to this reason we will say that the detected pulse is S1. Similarly, you can traverse the same flow by using the second pulse S2 by keeping the coefficients same. You see, the coefficients will not change. each branch is dedicated to a particular transmit pulse. It is matched to one of the transmit pulses. The only thing which will be changed are the contents of these two registers, the register 1 and register 2. These two registers will change their contents to proceed with the detection. So this was specific to binary. If you talk about the coherent detection of M-array phase shift keying, if you generalize the concept, so what is the main theme? The main theme will be, because it is using two basis functions, two-dimensional modulation scheme, so the correlator structure will have two branches. In one branch it will be multiplied with psi 1, in the second branch it will be multiplied with psi 2, right? And if you remember, what was psi 1? Psi 1 was simply Es multiplied by cos of phi I. And what was psi 2? Psi 2 was Es square root multiplied by sine of phi I, right? So what we are doing basically, we are multiplying the received signal. If you look at this phasor diagram, in one branch we are multiplying this R with cos phi I. In the second branch we are multiplying the received signal R with sine phi I. So this is the horizontal projection. This is the vertical projection corresponding to the angle phi I. This is the angle phi I. So if we want to have an estimate of this received phase, what we will do? We will simply take tangent inverse. Because you see, here we are getting this thing, here we are getting this thing. So at the sampling period, after accumulating all the result over sampling period, we will compute simply tangent inverse of these two branches. So you can say here in this triangle, we are taking tangent inverse of y over x, vertical component divided by horizontal component, to generate the estimate of the phase. So at the output of this arctan or tangent inverse, we will have the estimate of the phase. Now we have already got the actual values of all the phases. For example, if you are talking about quadrature phase shift keying, QPSK means m is equal to 4. So all the phase values are 0, pi by 2, pi, 3 pi by 2. We have got these four values. So we will only compute the difference, the absolute difference between the estimated phase and the phase already known by the receiver. So it will compute four differences in case of QPSK, and it will decide the symbol for which the difference of the phase is minimum among all, right? So choose the smallest. That is the reason why. So this concept can be further understood by the help of constellation diagram. Let's say I am again drawing the constellation diagram of QPSK. So in QPSK, you see this is phi 1 of t, this is phi 2 of t, and these are the four symbols. These are the four symbols, right? This is 0 0, this is 0 1, 1 1, and 1 0, assuming gray coding. What are the decision regions? Equally spaced decision regions can be formulated as this one. If I just draw lines here, then this particular region is the first one, this particular region is the second one, this region is the third one, and this region, the blue one, is the fourth one. So we have got four decision regions. For example, the received symbol impinges here in the form of a star. Now you see, we will find its angle. Let me use a different color over here. We will find the angle of this received symbol. This angle of received symbol is basically phi hat, right? So this phi hat will be compared with phi 1, phi 2, phi 3, and phi 4. It will be compared, and the symbol will be decided for the smallest phase difference. Right? So in this particular case, you can easily see that the detected symbol will result in the symbol 1 0. This symbol will be detected because it is nearest to the angle phi 3. If we say this is phi 3, so phi hat is very close to phi 3 as compared to all the other angles. So that is basically the proper operation of this particular MPSK scheme, and we have already mentioned that we have used coherent detection to perform this demodulation, because again it is using phi 1 of t and phi 2 of t, and both these are involving the carrier phase, right? You see, this is the carrier phase. It is using the carrier phase for the demodulation. Due to this reason, this is called coherent detection of MPSK. So this is all about the detection of MPSK. In the next lectures, we will be discussing the second category of two-dimensional modulation scheme, which is MRE, quadrature amplitude modulation, MQAM. And further to this, we will also discuss the multi-dimensional modulation scheme, which is frequency shift keying. Thank you for listening.